we're deriving the spin coherent state, and we're defining an operator that's basically the SU2, group. So rotations under the special unitary SU2 group, and that's what defines your quantum. Basically your arbitrary quantum spin with 3 components. So that arbitrary rotation is written in terms of these Euler rotations. And as you know from classical theory of angular momentum or rotation, or wherever you've seen this before, you just use a Z, Y, and a Z operator, or Z, Y, and Z rotation, and all you do for the SU2 is just replace those with the operator. Okay, so that's SU2. That's an SU2 spin, quantum mechanical spin, and we didn't prove this identity, but we're going to use it to derive the coherent state by considering an arbitrary rotation, this unitary operator transforming an SZ spin. So that's what I started with last time. It was R. Let's see, R. SZR. Oops. Okay, so this involves writing all these operators out. So bear with me while I do that. I'm going to drop the hats. Phi, theta, chi as Z. And let's see, minus signs. And for the adjoint operator, complex conjugate, reverse the orders. So chi, theta, phi, Z, Y, Z. Right. Okay, you'll do a lot of manipulations with expressions that look like this. All you have to remember is that when you have an operator in an exponential and that same operator, these commute, right? Again, the exponential is defined in terms of its Taylor expansion, so you can imagine just Taylor expanding the exponential, commuting SZ through. And what you'll get is, in the end, these two terms next to each other, and that'll give you unity, the unity operator. So every time you commute, you can simplify a lot of these expressions. This one will give you just the first two terms, then the SZ operator, and then I, theta, Y, phi, Z. Now you're in position to use this identity. Okay, so just keep the order of the permutation of the indices in mind. I, J, K, if you permute any of the indices, you get a minus sign from that Levi-Civitas symbol. So in this case, your I is Y and your J is Z. So your K should be X. So all right, that's those middle three operators. And then e to the I, phi, Z. Right. All right, cool. So let's see. Let me just write this out, expand this out. So, right, you have an SZ operator, which commutes through this exponential. So you can write it like this. And this one's multiplied by, oh yeah, I, phi, SZ. I could have got rid of those. Then I have SZ, SX, and then I, phi, Z, Sine theta. Okay, we use the identity again on this term here. These things will give us unity. And a sine theta. Okay. And let me just order this in terms of the operators. So Sx cos phi sine theta. Sy sine, too many thetas. That should be a phi. Sine phi sine theta. And then Sz just says it's cos theta. So what does that look like? It looks like the spin operator. Remember, these are all operators. They're the three operators that make up what we call the spin vector, I guess. So this just looks like S with a dot product of, the unit vector, which I'll just call omega. And that unit vector is just, the angle of the final rotated spin. Okay, so you imagine starting with some spin, applying this SU2 rotation defined by R, and this transformation of the SZ operator just gives you S dot product with that unit vector, which defines that final direction. Okay, so with this we can define what the spin coherent state looks like for us. I'll call it G. I don't know why. You could call it omega, or some textbooks call it like N, because, well, it's like a unit vector. So the coherent state depends on these angles, and it's defined as this arbitrary rotation. I'll write it like this. That's your spin value, and that's your maximum eigenvalue, or your maximum eigenstate of the SZ operator. So you could also write it like R, S, maybe arrow up. Okay, and this will become apparent why we choose this as we go on. So, so it's relatively easy to remember. It's just a spin eigenstate, right? This is the eigenstate of, this gives you the eigenvalue of S squared. This is the maximal eigenvalue of SZ, but we applied this arbitrary rotation to it. And this thing, which I call G, is what we're going to use for the spin coherent state. And the way we'll use it is by applying S dot omega to it. As an operator, which is exactly this thing here, you know. Which is R SZ, oops, R dagger, the adjoint, applied to G. Let me just take advantage of the fact that G is defined with this R here, so R SE, R dagger, R G. Right? So then the adjoint and the operator give unity, and I'm left with something that looks like R SZ. So this should be not G anymore, right? This is S. What I'm calling S and plus S. So I have S plus S. Right. And I can operate with SZ on this ket to just pull out that maximal eigenvalue. And it's just a scalar now. It commutes through. So I should have S, R, which just gives me G. So it's a little different than sort of the coherent states that we've defined before. So previously we had coherent states such that the raising or lowering such that the lowering operator just gave us an eigenvalue straight up. We just had an eigenequation for A, right? The annihilation operator. Here we have something a little different. We're defining coherent states in such a way that we essentially have this property. When we apply this operator to them, right, they give us back the maximal eigenvalue of SZ and the state back again. So G's a little bit different. It's more like the state with the maximum, I guess, spin projection along the axis defined by that unit vector omega. If you need an interpretation. Omega axis. So what we can imagine the path integral being now is really just, you know, the imaginary time evolution of, say, this omega unit vector as, you know, as a function of tau or whatever. So the path integral will be somehow, you know, the time evolution or the imaginary time evolution of this angle or this projection. So just imagine I'll draw this later in the path integral. That's what we're building towards, these coherent states. So So just one observation about the angle chi up here. I have a theta and a theta and a phi, but you need 3 angles for this arbitrary rotation, right? So to define an SU2 invariant spin, this is the SU2, this is operations under this SU2 group. You need these 3 different angles, but that chi is somehow special. Because this first step, when I just commuted this operator through, and I had the 2 exponentials right beside each other, which gave me unity, just basically got rid of that angle. Right? So as long as chi is the same in both R and R dagger, it falls out of the expression for the coherent state. So the reason is, if I write this coherent state, if I write out this R operator, let's see, I theta S Y. That's my R operator. And S and the maximal eigenstate of SZ. So the first thing that happens is this operator just pulls out the eigenvalue, because that's the associated quantum number, right? So this just gives me something that's got the angular dependence I theta sy s plus s, and this thing, which is just a scalar now, just a C number. Whoops. So all it's doing is multiplying your state by some overall phase factor. So you could call this state G tilde and a phase, if you wanted to. All the angular dependence is just contained within that G tilde. Chi is called a gauge factor, but it's just an overall phase. Okay, so even though it appears in the general statement for the SU2 rotation, it doesn't have much effect on the coherent state. And in the end, what happens is, Hamiltonians are invariant under this type of gauge, under a gauge transformation defined like that, a U1 gauge. So we have a picture where we're really tracking the angles, theta and phi. X, Y, and Z. How does this work? So phi is defined, okay. Yeah, so theta is defined relative to this z-axis, right? So theta is, which one's theta? This one's theta, right? And this one's phi here. Why, that's not perfectly clear? God, you guys. It's perfect. Whoa. I just got to remember which one's defined in the interval 0 and pi and 0 and 2 pi. So it must be like this, 0, 2 pi. Yeah. That becomes important when we do the Berry phase. Yeah, and so what chi is just like, another rotation around that vector that basically doesn't give you anything. So it's a redefinition of your coordinate system. So it's looking like the path integral is somehow going to resemble the path of this purple vector around the 2-sphere. Okay? We'll talk about this phase some more. So there's a subtlety, which is the Berry phase, but otherwise what we're looking at is like just this purple vector moving as a function of time around this 2-sphere. Okay, so we have the coherent state. We need a couple properties of the coherent state in order to construct the path integral. What will we need? We probably need the overlap and the completeness relation. So okay, so there's an issue with orthogonality of this coherent state. So actually, if I have two different coherent states, G and G prime, they're not orthogonal. So that's a thing. You can just write it out. Call it G, I don't know, G prime. So it's chi prime, theta prime, phi prime. That's what defines two different states. It's two different angles in this unit vector, if you will. So this will give you something like, you have a phase factor, which you can always pull out, but you have two different chi's. So their difference appears in the phase. And then S plus S. I think I did this right. E minus I theta. Oh, I forgot my operator here. S Z. I don't know, I'm not calculating anything. I'm just showing that this generally isn't zero. So I have to worry about all these angles and everything. But at least when the angles are the same, right? Chi equals chi prime, phi prime equals phi. Then you get unity for all these things. And, the overlap is 1. Okay, so That's important. And the thing we really need for the path integral is the completeness relation, so we can insert resolutions of the identity willy-nilly into the exponentiated, partition function, whatever you want to call it. So that's the second thing. The completeness relation is really difficult to calculate. It would take me the entire class. So it's going to be on your homework. And you guys get to do it. So you'll do with Schwinger bosons. There's two different ways to do it. Well, I know two different ways, but you'll use Schwinger bosons and basically do this for your assignment question. With okay, so let me write the answer that you'll get. What's going on with these chalkboards, man? Okay, so it turns out it'll look like this. Okay, this has to be theta. All right, sine. Yeah, that's right. And then chi. Or you could write this in a different way, I guess. So it'd be 2s plus 1. Yeah. And that Jacobian, or that measure of integration, is something to make note of too. You can drive it in group theory, or I think you'll do it on your assignment. It's called the Haar measure. S plus 1, 4 pi theta, right, sine, oops, d phi. Okay, so that's called the Haar measure of the SU2 group. So have fun with that. So I'm just going to use this now when I make the path integral, okay? So I think that's basically all we need. I guess we'll have to assume some form for the Hamiltonian. But let me worry about that a bit later. Okay, so with the coherent state and with its properties, let's discuss the path integral. So let's construct it for the partition function. Which means taking the trace e to the minus beta h and breaking the exponential up into small steps, delta tau, which run from imaginary time 0 to beta. And then we're going to substitute in between every one of these resolutions of the identity. So all that's the same, and in the end what you need to do is calculate the matrix element, just like we have before, of this operator, right, in between, a Brownlee-Ket defined by that resolution of the identity. And hopefully we've constructed these coherent states such that, the matrix element of the Hamiltonian gives us something nice. So we're going to look at Hamiltonians that are sort of the typical Hamiltonian for spin systems. So hopefully they contain the spin operator, something like B dot S. B is a magnetic field, right? You can have some sort of time and space variation in your field, or it can just be a uniform external applied field. But at least it has a spin operator. Or it could be something like you're deriving on your assignment. That's like S dot S. For two different spin indices, for example. But let's construct the path integral first, and then we'll examine exactly how the matrix element for these different types of terms looks. Okay, so let's look at this matrix element. So we assume delta tau is infinitesimally small. Remember this partition function, this is true in the limit. Basically when delta tau is very small, and we use that to define the functional integral. So I can expand the exponential, 1 minus delta tau h g tau. And remember, I have two different time steps because these come from two different resolutions of the identity. It's like if you insert one in here, then you have to insert another one on the other side, right? And they have a different index, or they have a different, and imaginary time. So let me write this matrix element out. That's the first term. That's 1 minus delta tau. Hamiltonian G tau. Okay, I'm going to do something that feels sketchy, but I don't know any other way to do this. So I'm just going to add 0 to this thing. And by 0, I mean I'm going to add 1 minus my assertion here. That G, if G and G prime are the same, then the inner product's 1. So that's 0. And then plus this term minus this term. And then this term here minus delta tau. All right, so this is just my matrix element. This is what I'm going to handle a bit later. But I'm assuming somehow I have a Hamiltonian that's going to operate on that coherent state in a nice way that makes this understandable. I don't know why I think this is weird, but I'm just going to re-exponentiate this thing. So I just have 1 minus something, right? So this is just going to be exp g tau plus delta tau. That's this term. I'm going to minus this term just to write it in a different way. And then minus delta tau. And then Hamiltonian operating on G tau. I don't know. How does that make you feel? I guess it's okay. The reason I feel weird about it is there's no delta tau in front of these things. So it's like they're not small parameters, but I feel like I've done this before and it works. All right, so let's just keep going. So this will give us the partition function. That's like the only hard step of the path integral now is to essentially evaluate this matrix element, right? So I'm going to take that final limit, where all these delta taus go to 0, and then I write this as functional integral. That trace is like, right? So now there's a product of a whole bunch of sums, right? That's what I write as curly D. It's a functional integral over all these coherent states that I've inserted. All right. Okay, and I have to worry about my delta tau integral. So let me pull this out. I'll still write as a discrete sum over taus. Now I'm going to have something like this. Make sure I get these signs right. Okay, I just pulled the delta tau up front so I can divide this whole thing by delta tau. Your small imaginary time step. Okay, that comes from the first two terms here. that minus sign should be, I think, overall, right? Because those things have different signs. I don't know why I pulled that out. Oh yeah, because I have minus delta tau. Yeah, then I want to just write this term. That's right. Okay. So it's like this. Plus, yeah, G tau plus delta tau. H operating on G tau. Oh. Like that, okay? So I've just set that up so that you can take the limit of delta tau goes to 0 and then turn this thing into an integral. No, sum, not the integral. And those taus are summed up from, we introduce an index from 0 to beta, so the integral's 0 to beta. Delta tau gives me dt, d tau. And then we get the time derivative from this term, right? Just like before, so, oh my god. I'm gonna write it like this. Tau plus delta tau. And G of tau. Right, so that's the thing that gives you a time derivative. So it's a time derivative in the broads. So you can write like d tau, G, something like that. That's exactly analogous to the I p x dot that we did, that we derived for the position momentum space path integral, the single particle path integral. This is a single particle path integral too. It's just a single spin. Okay, so we're going to be able to write the path integral in a nice compact notation again. But like always, that notation means nothing without interpretation, so we'll look at the various terms. So Z will be, right, so the functional integral. And then minus 0 to beta. Okay, so I need this, let's see. I got a minus. Right. So I always have e to the minus sort of actions. That's why I have a minus sign there. So I just got to keep track of these minus signs. So I should have this. The time derivative. And then just the matrix element of the Hamiltonian. And that's it. Okay, so that's like the quickest way I could derive the path integral. So the only subtlety is sort of what's going on with this thing, I think. So it's compacted. Let's separately look at both of these terms and try to interpret what they mean physically in terms of the spin evolution, if you will, in imaginary time. Okay, clear up to this point? This makes sense? This is starting to look familiar? you're comfortable with this. So let's look at the consequences. And this is your action. We can call it S. Look at these two parts of the action separately. So I'm going to start with the Hamiltonian piece. I still have it written in terms of an operator H. All right, so we have to think about what that matrix element looks like. So I could have Hamiltonians that look like, I don't know, something with spin operators, like I was saying. But in order to do this, we need to know somehow what the matrix element of the spin operator looks like. Okay, and we can just calculate this component-wise. So X, Y, Z. So let's look at those three components. We have to think back and remember what G is. You have a question?
Yeah, I'm wondering why in this partition function path integral we don't have the imaginary unit with this inner product of delta tau G and G.
Why philosophically, or why?
Well, why doesn't that appear here?
So it will appear. It'll appear when we look at what this means, I think.
Okay.
Yeah. So you'll see an imaginary number in the action. So let's just leave it like that for now. But yeah, why does it occur in the Feynman path integral? I forget where it pops out, actually.
Well, it pops out when you do your Wick rotation.
That's right.
Yeah. So
there's something, I think it's the same. I think it's just hidden inside there.
Yeah.
That's the same term. That's what I was calling the Berry phase before. Today we're going to see why it's a Berry phase, that piece. So we'll look at it quite a bit. This term, the second term, I think it's somehow simpler. So I think as long as you have spin operators in your Hamiltonian, it's going to have a very simple form. So we'll come back to the Berry phase in a minute. So let me just write this as. So I need my R, my rotation operators. And these are the same state. So I'm going to throw out that overall phase, that chi. So I'll just have theta phi z, right? Should be minus, reverse the orders, I theta sy, s plus s. I already dealt with this thing before. All the operators are the same. Just commute two of them. Pull out that unity. S plus s. Theta. Right. So we need that identity again. So it's Z and Y, so you get X out front, sine theta. I feel like I fudged a minus sign there. Did I? Oh yeah, the minus sign is right in the identity. The minus sign occurs on the left-hand side. So we can absorb a minus sign into the definition of theta, I think. So let's keep going with this. And if I drop a minus sign like tomorrow, remind me where it came from. This is an operator operating on this state. It's an off-diagonal operator, right? So without much proof, I'll assert that this is 0. So this term is 0. And so all we're left with is S cos theta. And I think that's fine. I remember I said the coherent states weren't necessarily orthogonal, but this is just a regular, there's no angles in that state, so this is just a regular spin state. So the matrix element of the first, or the Z component, gives you S cos theta. And S is just, again, the maximal eigenvalue of that operator, SC. I could do the other two components, or we could leave 10 minutes early, so I'll just write them down. Because I think there's no tricks. The only thing to note is that you'll get phi dependence. So it should be cos, then it should be sine. Sine. Yeah. You can do that when you're bored. Just write out just write it out the way I did over there. So then, so if we write this component by component, we'll recover all the components of the unit vector. I think that's no surprise. So every time we have a Hamiltonian that has, this spin operator in it, and we apply to the coherent state, the matrix element will give us this back. So with this, we can write the action for all the Hamiltonians that we're essentially going to be interested in. At least we can write the Hamiltonian part of the action. Okay, so for example, if I'm h dot b, it's simple. All you get out is SB and the angle between B and omega. Yeah. Then G, HG. Which is just S B dot omega. So what you're keeping track of with that term is the angle between, so whatever the magnetic field is, if it's uniform, you can just define it along the Z axis, right? And so all you're keeping track of is the angle between that axis and the thing that your path integral is, which is basically this angle, this unit vector, omega. So S B dot omega. It's like SB. Ooh. It is theta. Yeah. I don't know. Okay. So then the action just has that term in it. So the d plus one dimensional path really just tracks this angle. That's what your path integral, that's what this piece of your path integral looks like. If you had S dot S, all that is a different angle that you're tracking. So the thing that you're driving on your assignment, the Hamiltonian, that's the low energy Hamiltonian. It's a low energy effective Hamiltonian for the large U case of the Hubbard model, right? The large interaction case. It has S dot S in it. So you probably had a J in front. That's some factor of T's over U's. Nearest neighbor lattice sites, just like we use for the transverse field Ising model. And you have something like SI dot SJ. So if that was your Hamiltonian, then the many party, I mean, I have many particles here, but the sort of many body path integral is just an extension of what we're doing. So you would get something like, let's write the matrix element, I guess. J S squared, and then sum of all these angles. Unit vectors. These are unit vectors. Right? So the many particle path integral would have just a piece that tracks all the angles between all the spins. What does this strike you as? It's all completely classical, right? They're essentially completely classical Hamiltonian or matrix elements. They're just the angles between your unit vector that you're tracking as a function of imaginary time. And so that second part of the action, the piece that comes from, you can write whatever your favorite Hamiltonian is here, is really just indistinguishable from a classical, a classical Hamiltonian. So without the Berry phase, then the partition function Z it's still d plus 1 dimensional, but your classical to quantum correspondence is basically perfect in that case. So we better hope that all the quantum mechanics of our spin, our single particle spin, is somehow contained within that Berry phase. So the question is, what is the quantum mechanics contained by that Berry phase? Okay, so let's look at that. So we're going to call that second part of the action up here the top, or the first part, the topological piece. And you'll see why in a minute. So forget the Hamiltonian piece. Let's look at the topological piece that's written in terms of these two angles and parameterized by imaginary time. Di tau g g. Okay, so let's think of what's going on with that time derivative. Sorry. So I'm going to write out my two g's. Remember, I have that phase factor, so let's be careful and include it. We'll include the chi. So we'll get something like time derivative. Yeah, let's just pull that thing out first. So e to the minus. So it's I chi sz operator, right? So I can just pull out I, the eigenvalue s in chi, and then that thing I called g tilde, which just had the two angles here. And then e to the so I'll take the time derivative of this angle first, right? Then I'll take the time derivative of the rest of it. So I'm going to have two terms, actually. So it's time derivative of g tilde minus is, and then the time derivative of chi. Right. But now we get to use the fact that we're calculating the partition function. And our path, in our path integral, is periodic in beta. So the path will close on itself. So we're imagining going around that unit sphere. We're dragging around this additional phase factor. And in order for us to, respect the condition of the periodic boundaries that come from the trace, we'll just make sure that all these angles are periodic in 0 and beta. So that when I take this integral, so I have a tau integral of the tau derivative, right? Where the endpoints are the same. So that integral is going to kill that time derivative. So the path integral doesn't depend on that phase factor. I pulled it out here. I'm using G tildes. This is the last place where that phase factor can occur. So it's killed in this path, and that's why we don't have to worry about it. So it's looking more and more like our path integral is just paths living on this 2-sphere. Okay, so let's go back. Let's forget about that phase factor. Let's go back and look at the rest of the action. That was minus out front? Yes. Did I drop a minus sign somewhere? Here, maybe? So let's consider the time derivatives of this thing. Okay, so the way that like we had all those discrete time steps, and the way things shook out, that was the time derivative in the bra. But now our coherent state has a whole bunch of imaginary numbers in it, so we have to be a little bit more careful about how we handle this thing. So let's just take the time derivative by taking the adjoint of everything operating, if you will, forward on the ket. Okay, so right, I've gotten rid of chi, so that's just S. And the maximal eigenvalue adjoint. Let's write these terms out to be careful. So remember, so my operators aren't time dependent. Okay, I'm not in that picture. Okay, which that's Heisenberg picture or whatever. The only thing that's time dependent or imaginary time dependent is the angles that occur in this unit vector. So that's what my path is describing. So I have these two time derivatives. And I pull down an SZ there, and I pull down an SY here. And I have my state plus S, all adjoint. Okay, so let me just take the Hermitian adjoint and then look at this inner product here. So that's the time derivative in the bra. So all your i's go to minus i's. I guess that's it. Because your operators are all Hermitian. Theta phi. That's the first term. I goes to minus I, so I have plus theta sy I phi sz, right? So reverse the orders. Okay, right, so that's just the bra. Now the ket is this G thing. Okay, so S plus S. Sweet. So you see a first term here. You have an exponential written in terms of SZ operator. Commutes through. It's going to give you unity when it hits this bad boy. So then all you're going to have left is this thing here and the time derivative. What happens here? Here, same thing with these two. And then these two are next to each other, so they kill each other. So you get a really simple expression in the end. This is going somewhere important. Promise you. I promise. Okay, so that's my time derivative. E I theta sy. It's my first term. Theta, theta, right? And then sy, everything else canceled. The final thing we have to do is use that identity again, because we have y, z, and y here. So that gives me z and then x, right? I think I got the signs right this time. I don't know, I wrote this all out, but in the end, I have the matrix element of SY, which is off diagonal, SX, which is off diagonal. So the only thing I'm left with anyway is the Z component. So I should have I. SZ operating on that state returns that maximal eigenvalue, cosine theta. And I need this time derivative here. Okay, so that started out messy, but it ended up nice. So that whole topological part of the action is just this time derivative. All right, in terms of the tildes. So it's minus I, S, 0 to beta, d tau, cos theta. And then it's d theta, d tau. So the reason that's important is because, we always have velocities. We have x dots and p dots and stuff in these Berry's phases. But here you'll see that you parameterize this thing in terms of tau, but you don't need to, right? You could just parameterize this angle in terms of phi, right? So you just have a unique parameterization of theta and phi. And what I mean by that is just cancel these things, right? So somehow the Berry phase no longer depends on depends on any of the velocities or the time derivatives anymore. And that's why it's called the geometric phase. So we have to write the thing now is minus I, S, integral, but now you have to have the values of phi at tau equals 0 and tau equals beta, and it's periodic, so they're the same. And then you have to write cos in terms, or theta in terms of phi. Question? So it depends on the trajectory only of, you have your sphere and you have your unit vector. And that thing's tracing on a path that's periodic, however it looks. And this Berry phase only depends on the geometry of that path, not the speed at which you trace that out, basically. So its tau dependence doesn't come into the picture. All right, I lied about going 10 minutes early because I'm so excited now. I just want to finish up this Berry phase. So you have this expression for a Berry phase. Where does the quantum mechanics come out of this? It's geometrical, okay. But we're worried now that these terms of the Hamiltonian only give us a d plus one dimensional classical spin. So let's look a little more closely at the area enclosed by that path. Okay, so your path integral is is sort of the tau evolution of this thing that must close on itself in the unit sphere. So that encloses an area, a surface area of the two sphere. Okay, so if you have a sphere and you have the North Pole and this path, let me just draw this path like this, I don't know. The area element, so let me calculate this area element. I can have this parameterized in terms of sort of my d theta. It's my theta angle. Which one is theta? Theta is the one going around this way, right? So this is my theta angle here. And I have some infinitesimal time evolution of my path. You know, this point and this point. So the solid angle between the z axis on the sphere and these 2 points on the path is easy if you know stuff about curved coordinates, which I don't. So I found it in a textbook, and I'll call it small omega, where I'm integrating over basically just the Jacobian there. Which gives me 1 minus cos theta d phi. Or I could have this parameterized in terms of tau d theta d tau d tau. So if I integrate this in terms of tau, that gives me my closed path. Question?
Can you have like more complicated paths that like cross themselves, or?
Yep, in principle.
Does that mess up your calculation?
It gives you the thing I'm calculating. The solid angle can only be defined modulo 2 pi. So the area has a limit, or sorry, 4 pi. 4 pi is the area of a sphere, right? So I'll talk about that, but I mean, I'm guessing because I never tried, but I hope it doesn't screw anything up. So this is just the like infinitesimal solid angle. So the full solid angle subtended by that path, defined via the point where the z-axis exits the sphere, is just the integral over tau, if you will. And that thing is just the same as this thing right here, except for that 1, which is secretly a 0 because the path is closed, right? So if I take the integral of that and the endpoints are the same, I can just insert a 1 there. So this is actually the same as, do I need a minus? Oh yeah, minus in front of the cosine. Since, look back at the phi parameterization, that makes a lot more sense. Okay? So that 1 doesn't affect us at all. So what this means is the Berry's phase is actually that solid angle. subtended by the path. That's why that's why they call it the geometric phase. So all the quantum mechanics is somehow contained within that geometric phase. So let me just call it S topo. You have to have that spin. Is that an S? You have to have that ISO front, and it's just IS omega. Okay, so just by identifying, you just have to know this, basically how this Jacobian works for curved coordinates, but just by identifying that integral with the second term of the action, we see that we're just measuring that area. So let me just show you how spin quantization comes out of this. Because if I leave it till Tuesday, it won't make any sense. I could have defined that area by flipping my north pole to my south pole. Right? There's two different ways I could have defined my coordinate axis. That was just some arbitrary choice, right? So note, so I could have defined my z-axis this way. And then instead of measuring this as my omega, right? That's my integrated d omega. I could have defined same path. I could have defined this as my omega. Well, it's different. So call this omega prime. And you know it's going to be different, right? It's a different omega. Like it's a different area. So omega is not equal to omega prime in general. But if you look at your definition of theta, then I can rewrite that area element where I define theta through the south pole. So the z-axis here is the north pole. But if I redefine the z-axis through the south pole, then I could have the same expression. Let me parameterize it with phi. But now I need to define my angle. Remember, I'm traversing the same path. But instead of being theta down from the north pole, I'm pi minus theta up from the south pole. So you can write it like that. d phi. And all that gives you is minus cosine. Right? So that implies that this whole thing gives me minus s omega prime, where omega prime is defined right there. But the action should be invariant upon this choice, right? Your physics shouldn't care about how you arbitrarily define the north or south pole, or the z-axis through the north or south pole. So if I write that topological term, that should be true. And because we're on a sphere, we're on the surface of a two-sphere, these two things have to equal 4 pi when added together. Okay, because that's the total volume, the total surface area of a sphere. And that's it. Just that geometrical fact constrains your s's in this equation, right? So S, which is the maximal eigenvalue of the SZ operator, has to be it has to be 0, it has to be like 0, 1/2, right? 1, 3/2, and so on. So it's n/2 and integer. So that's why I went long to finish, but so the Berry's phase is just the lesson is this. The expectation value of the Hamiltonian just gives you a classical d+1 dimensional partition function or action. But the Berry's phase gives you this piece here, which you can interpret as being related to the surface area enclosed by that path, like the path integral path, which is just, you know, the locus of points moving around here is a function of tau. But because of the geometry of the two-sphere, because of the constraint of the surface area, and the ambiguity in defining, you know, you can define the z-axis anywhere through here, but the ambiguity of defining it upwards or downwards through that path just gives you the fact that these s is constrained. So the value of that eigenvalue is constrained to be half integers. So, you know, we started with just the commutation relations, and I didn't explicitly assume spin quantization anywhere. And the cool thing about the spin path integral is the spin quantization falls out of the Berry phase. Okay. So I think that's one of the most important lessons in this class, is that somehow the quantum mechanics is contained in the Berry phase. And here it's very obvious, it's the spin quantization. Okay. Questions on that? Makes sense? You seen that before? Okay. We'll talk a little bit about how equations of motions and so on arise, but this is the basic point that I wanted to get across with the spin path integral. After that, we'll move on to 5-4 theory. Okay? So we'll see you guys next week, I guess.